All right, welcome, ladies and gentlemen, to lesson 4 of Unit 3. This is the big one that's going to start speeding up all of our calculus processes. We're going to be looking at all of our rules for differentiation. We've been calling them tricks for quite some time now. Things that you weren't allowed to use yet, but now we are going to use them non-stop. So let's go ahead and get right into it. We got a lot of things to cover today. So first one, the derivative of a constant. So if you're given f is a function with a constant value, something along the lines of f of x is equal to 3. If I took the derivative of x, or derivative of the function f, this basically says the derivative of the constant is 0. So the derivative of the function with respect to x, given that that function is a constant, the derivative is 0. And that should make sense since f of x equals 3 is a horizontal line. The slope at every single point is 0. That should make sense. Okay, that's the first one. That's a simple one. Second one. This is one of the best rules ever. This is the power rule for positive powers of x. If n is some positive integer or some positive number, then the derivative of that function looks like this. X to the n, the derivative of x to the n is equal to n times x to the n minus 1. And you may have started seeing that pattern. If f of x is equal to x squared, the derivative of x squared is, let's see, that 2 goes to the front, and you reduce that 2 by 1, which is what this is saying, becomes 1. So the derivative of x squared is 2x. If I give you the function that is x to the 5th power, this g prime of x, the derivative of that is going to be, okay, the 5 comes to the front, and we reduce the exponent by 1. If we have h of x is equal to x, h prime of x is going to equal, okay, that's x to the first. So I need to bring the 1 to the front. This becomes reduce the exponent by 1, so I get 0. So it's 1. The derivative of a linear function, this linear function is 1. Isn't that so awesome? We don't have to use the limit definition here because we've used it, we know it. Now we're going to use the tricks that come from the limit definition. Next, if you have some constant multiplied by your function, you can essentially take the constant to the front and take the derivative of the problem itself. This would be something like this. F of x is equal to 3x to the 4th power. If I took the derivative of this, this would be 3 times the derivative of x to the 4th. Well, that's 4x to the 3rd, which becomes 12x to the 3rd power. And you start seeing how handy these properties can become because trying to do the limit definition for x to the 4th power is very tedious. Very, very tedious. Okay, some of these look like they're all kind of disjointed rules, but they all actually go together very well here as we go into the harder and harder problems. If you have two different functions and both of those functions are differentiable, then their sum is also differentiable, or their difference. And we can say something like this. Now, this might look like a bunch of chicken scratch to you, but this is what this means. If f of x is 3x to the 5th minus 2x to the 3rd plus 6x minus 7, we can now use all 4 of these rules to take the derivative of f of x. Because x to the 5th x to the third, and x and the constant are all differentiable functions by themselves, I can take the derivative of each of these pieces separately, which is what this is saying here on the right, and we just learned that we can have the constant multiple of a function and take the derivative. So this becomes 3 times the derivative of x to the fifth, which is x or 5x to the fourth, minus 2 times the derivative of x to the third, which is 3x squared, plus 6 times the derivative of x, which we said was 1 a few minutes ago, minus the derivative of minus 7 is 0. And we simplify this to say this is 15x to the fourth minus 6x squared plus 6. And there we have the derivative of f of x from a very complex problem if you were to try to do the limit definition. Now that should just blow your mind. We've spent weeks on the limit definition, or a couple weeks, and when it comes to this type of problem, it takes about 2 seconds. Once you get the hang of a polynomial function, it gets to be 2 seconds. But there's more rules. That's only number 4. And those 4 rules kind of combine together to help us take the derivative of polynomial functions, among others, but mostly polynomial functions. But now we have other types of functions. We could have the product of 2 functions. If we had the product of 2 differentiable functions, what this is saying says the derivative of a product is the first function times the derivative of the second plus the second function times the derivative of the first. So if I wanted to find f prime here, I would think of this as function u and this as function b. So I need to take the first function, multiply it by the derivative of the second. And the derivative here is going to be 3x squared plus 0. So that's going to be 3x squared. Plus the second function, or my v function, which is x cubed plus 3, times the derivative of the first, which is the derivative of x squared plus 1 is 2x plus 0. And I could simplify this if that was really the point. I wanted to just prove how to find the derivative of this function using the product rule. Now you might see that that's not the only way I could do it. F of x could actually be written as the product there, which is x to the sixth plus x to the third plus 3x squared plus 3 if you foiled those two things, and then you would even have to use the product rule. But there's some problems that don't work like that, and the product rule is super, super handy in order to find the derivative here. All right, products wouldn't be anything without quotients. So we also have a quotient rule. This one's going to look a little bit complex, but it's not that bad. As long as you don't get v equal to 0, that's my denominator. The derivative of a quotient looks like this. U is my top function, v is my bottom function, or my numerator, my denominator. So it's denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the square of the denominator. Little thing that I remember learning when I was taking calculus was low d high minus high d low over low squared. So it's low, the bottom, derivative of the upper, minus the upper times the derivative of the lower times the lower one squared, denominator. So given this function here, I know we're rushing through this a little bit, but I think we can find the derivative of this pretty quickly using this newfound rule of ours. The denominator here is x squared, and if you think about this as a v and a u, x squared plus 1 times the derivative of the top, well, that's 2x, minus the top function, x squared minus 1, times the derivative of the bottom, which is 2x, all over the bottom function squared. And again, we could simplify this if we wanted to, but in this particular case, for the notes, we're not going to. We're just showing the process of the rules. All right, continue on. That's only number 6. See how many we got today. Oh, we got equations of a tangent. There's another rule coming up. I forgot I put this in the middle here. We could find equations for the line tangent to the curve at certain points given this particular function. We want to find the derivative of y to find the slope of the tangent line, because that's what the derivative says, at the point 1, 2. So let's look at this as the derivative. Y prime is going to be the top function, or sorry, the bottom function, times the derivative of the top, which was 2x, minus the top function times the derivative of the bottom, which is just 2, all over 2x squared. Now, we do want to simplify this one because we're actually going to plug in some numbers, or a number. This becomes 4x squared minus 2x squared minus 6 all over 4x squared. 4 minus 2 is 2 over 4. That becomes an x squared minus 3 over 2x squared. Sorry, yeah, 2x squared. I canceled a 2 out of everything. That really became 3 and a 1, which made, a 2 and a 1, which made a 1. 6 became a 3, and the 4 became a 2. But now I need to find the slope. So I need to find y1 at 1, which is 1 minus 3, which is negative 2 over 2, which is negative 1. So the equation for the tangent line is y equals negative 1 times x minus 1, because the coordinate has been given, plus 2. So that is point slope form and done. And guess what? You'll be asked to do this quite often. Find the slope of the tangent line at find the equation for the tangent line at a particular point. We can't do this one just yet. I realize I put this out of order. The last rule here is going to be negative exponents, because we need them. They follow the same power rule as long as x doesn't equal 0. So, if we were to have f of x is equal to 1 over 7x, and we didn't feel like dealing with the quotient rule, we could write this as 7x. Oh, we can't do that. Hold on. Oh, let's pause, rewind, erase pen. Let's just deal with it for the most part right now as 1 over x. This is actually x to the negative 1 power, which means f prime of x is equal to negative 1 x, and then we got to reduce this by 1, so we have to subtract 1, which becomes negative 2, which actually creates the answer of negative 1 over x squared, and that's actually the derivative of f of x. Now, we can do what I was drawing a second ago, but I forgot the way I wrote it. If I wrote 1 over 7x squared, I could rewrite this as 1/7 x to the negative second power, And therefore, g prime of x would be, okay, bring the 2 down, so it would be negative 2 over 7 times x. Okay, reduce it by 1, which becomes negative 3, which I could rewrite then as negative 2 over 7x to the negative 3 third power. So it follows the same thing. We have to say that x can't be 0 because then it wouldn't work if x was 0, obviously. So you can't find the slope of the tangent line when x is 0 here. Now, there are higher order derivatives that we need to pay attention to. When we look at y prime or dy dx or f prime, that's called our first derivative. Now, there are things like a second derivative. And it looks like this. These are the 4 different ways we could write it. So the first one being y double prime, saying dy prime is the derivative of y prime with respect to x. Or we can say it's the derivative of the function where that original function is dy dx. Or we can say the second derivative with respect to x. And it just continues that way. We say the third derivative just would be y with 3 primes on it. We would say it would be dy double prime. It would be the derivative of the second derivative. We could say it's the derivative of the, actually we could say it's the derivative of dy dx. We take the derivative of y with respect to x, then we take the derivative of that, then we take the derivative of that, and we could continue this to d3y over dx cubed. That would be third derivative. We could say fourth derivative, but when we get to fourth derivative, we would say y4 like that. But the problem with that, when people start thinking that is the fourth power, we have to start understanding, we don't usually write that. We would say f4 of x. We would say that's the fourth derivative. We don't get into fourth derivatives too often, but it is a possibility. All right, that was a lot of stuff. Hope you took a lot of notes. I'm going to leave you with this, and I will see you guys tomorrow.